Alright, so welcome to our next video on rational functions. I'll try and keep it short, but basically we're going to be focusing on the end behavior of rational functions and the related asymptotes. You should have already learned something about vertical asymptotes and discontinuities. If not, I suggest going back and looking at that first. And hopefully you remember some of your end behavior stuff from polynomials. Alright, let's do it. Alright, so this would be a typical graph of a rational function, and we've talked a little bit about what's going on here before, but what I want to draw your attention to is the fact that we have here a horizontal asymptote. And if you look at this, you'll notice that it's related to our end behavior. Alright, so as x goes to positive infinity over here, so you'll notice that as you follow the line, it's actually going to particular value. It's getting really close to this asymptote, which is at y is equal to 2. And if you travel backwards along this function towards x is negative infinity, right? Again, it's going towards this asymptote. So what we can see here is that for the ends, right? For the end behavior here, on rational functions, we're actually going to an asymptote that's going to describe both of those. So that's interesting. All right. So the end behavior of a function can be described as a horizontal asymptote. For this one, it's at y equals to 2. So let's look at this one. Now we have two rational functions here, the one we already looked at and this new one here. And remember that this is, since we're looking at end behavior, we really don't care what's going on here in the middle. We don't really care about this on either one. For both of them, we're saying, what is this thing doing as x gets really big, right? As x goes to positive infinity here. And you'll notice that for both of them, that we have, as x gets big, we get y is equal to 2 actually for both of them. So even though they looked really different in the middle, it doesn't matter when it comes to end behavior. So the end behavior here is at y equals to 2, and the same here, despite the fact that in the middle they look quite different. All right, just do me a favor, be really careful. Do not confuse this end behavior, these asymptotes that describe end behavior, with the vertical asymptotes that we've learned before. Remember that your vertical asymptotes here, right? This comes from discontinuities, right? It's going to be totally different. All right, so what we want to do is we're going to look at a couple examples here. So first of all, we have a rational function. You'll notice that we have a horizontal asymptote describing the end behavior right there at y equals to 0. Or we can have a horizontal asymptote at a numerical value like y equals to 2. Or we can have now this actually isn't a horizontal asymptote, but you'll notice that as x, in behavior wise, so if we're looking over here, you'll notice that this equation approaches this asymptote there. So we still have an asymptote describing the end behavior. It's just called a slant asymptote instead. And what we're going to do is we're going to figure out how to determine each of these from the equation of the graph. It's really good to be able to look at a graph and be able to visually see where your asymptotes are anyways, but at some point we want to develop the ability to do it from an equation. And you'll notice that this one here is a line. So since this is a line, y equals mx plus b, we can actually find the equation of that line. All right? So determining the end behavior from the equation of a rational function. Now remember that a rational function, of course, is a division of two polynomials. So we have the division here. So what we're going to do is we're going to create a simplified form based on the fact that for end behavior, we're looking at, well, what happens when x gets really, really big? So as it goes to positive or negative infinity. I recommend that whenever you're doing work, even when you're looking at an equation, please use a graphing tool. All right? Match what you're visually seeing to the equations that you're looking at so that you're checking and seeing that what you're doing makes sense. All right, so here's our example. So what you're going to do is to determine the end behavior, we're going to look at the ratio of the leading terms here. Now, why are we going to do that? So the reason that we're going to do this is because for very large values of x, the x squared term here is going to get really big compared to, like, for example, the -3. I mean, if you had this huge term, if you had millions of dollars, would you really care if you lost 3? Yeah, not really, right? So what we're going to do is we're going to focus on the leading terms here. All right, I know you guys can pause videos, so I went ahead and put that in there because for large values of x, the leading coefficients, they're just so much larger they dominate it. So what's going to happen, sorry, a lot of this came on the screen at once, we're going to focus on these leading terms, and it simplifies to this guy. Well, x squared divided by x squared is just 1, leaving us with y equals to 5/3. And what's neat here is if you look then over at the graph, we have this horizontal asymptote, and when I drew that line, it's at y equals to 5/3. It has an asymptote here at y equal to 5/3. So all of this said, what are we doing? You're just creating a simplified division problem. So let's try this one if that was too quick. So there's another one here. You have an example. Again, we're going to look at our leading coefficient. So that means we're just going to be looking at the -2x squared divided by x squared. X squared divided by x squared, and you're going to get -2. So from here to here, as x gets really big, y is going to end up being this. So we should have a horizontal asymptote at y equals to -2. Alrighty, so we examine the leading terms, and typed it out, so now it's all pretty. There you go. And y equals to -2. No surprise, I wrote the slides, so I should know what's happening, right? All right, so if we look at the graph here, you'll notice that we do end up, in fact, with a horizontal asymptote here that matches this guy at y equals to -2, and that came from this part here. All right. So now remember horizontal and slant asymptotes. So what we've looked at so far is this kind of middle case here where when we simplify the equation, we get down to a particular number and we have an asymptote at y equal to 2. Similar cases would be where you take that division, you simplify, you get y equals to 1/2 or y equals to 5, but you get a horizontal asymptote. So what we want to look at next is, well then how do we get these guys? All right. So both of the examples that we've looked at so far, and you can rewind if you need to look at them more, for both of these examples, you'll notice that the degree of the numerator and the denominator were equal. So you'll notice up here, the degree of the numerator and the denominator are equal. That's what allowed everything to kind of cancel out and give us a number. So what happens when the numerator and the denominator are different degrees? So our third example here was y equal to 1 over x plus 1. Well, again, we want to look at our leading coefficient, so this is going to simplify to 1 over x. And when we simplify it to 1 over x, well, that's not going to be our asymptote yet because we want to know, well, what's happening here. So we know that as x goes to infinity, x is going to get bigger and bigger and bigger. So, right, we got x and it's going to get bigger and bigger and bigger. And as x then goes to positive or number infinity, if you think about it, you're dividing by a larger and larger number. Well, this whole thing is going to go to 0. And that's what's written right there. Okay, so whenever you have one, it simplifies to 1 over x or 1 over x squared. We know that that's going to end up going to 0. All right, so let's go ahead and look at the graph. Oops, I'm sorry. Ah. So we're going to go ahead and we're going to look at the graph, and you'll notice that this number gets really big. The whole thing is going to go to 0, and sure enough we get a horizontal asymptote here at y equals to 0 because the graph itself is going to come down, and as x gets really big we're dividing by that number and it's going to go towards 0. Okay, so there are 2 more examples on this page. You're going to look at the leading coefficients here. So if you look at the leading coefficients, this part's going to simplify as x goes to infinity. Again, this is going to end up being a 1 over x, or really this should be a 20 over x. But even 20 divided by an enormously huge number is going to end up becoming 0 as that number gets bigger and bigger. So we look at our thing here, and it looks very similar to the last one. We get a horizontal asymptote at y equal to 0. All right, let's look at a little more complicated one. Leading coefficients. As x gets really big, that's going to simplify to negative 3 over x, right? Because these cancel. Negative 3 divided by x, this gets huge, so it goes to y equals to 0. And we get this guy here, and a horizontal asymptote at y equals to 0. Okay, so if you think about it, that handles. What I want to point out though is, what are we doing? We're just doing a simplified division. When we look at these problems, they are division problems. So it makes sense that they're going to act like a division of these leading terms as we move on. So in this case, I now have a numerator larger than the denominator. We're going to end up with this slant asymptote. So this is what I want to show you how to do. So in this case, when I go to look at those leading coefficients, right, as x gets really big, I can focus on the leading coefficients here, and I get 1/2 x minus 1. You're probably going, well, how the heck did you get that? So let me go back one here. So if you think about it, when we take that x squared divided by 2x, well, this is going to end up canceling. This is really 1x squared, so you get 1/2, 1 divided by 2. And then x squared divided by x is x. So we know that we're going to end up with a line, 1/2 x plus b. And how do we get the b? So this would depend on which teacher you're talking to. For me, I'm happy with the 1/2 x, but let's find the b. What you're going to do is you're actually going to do this as a division. I'm not going to, in this video, go through long division, but to get from here to here, you can use long. But from here to here, you can use long or synthetic division to end up getting the equation 1/2 x minus 1. And when you graph it, you get that this asymptote here is 1 equal to 1/2 x minus 1. So this, in summary, okay, horizontal versus slant asymptotes. It's all about the degrees, right? If you look at, if the denominator is larger, then you've got a small number divided by a large number, right? And we're just looking at degrees here. And you're going to end up with a horizontal asymptote at y equals to 0. If the denominator and the numerator have an equal degree, then when you look at this, it should simplify to 2 over x. The x's are going to divide out, and you're going to get 2. You're going to get a graph like this, where your horizontal asymptotes at y equals to 2. And if the numerator is larger, then you're going to end up, you could actually do, what this is doing is you actually could do this division. X squared could be divided by the 2x. So you're going to end up with a slant asymptote, and here, we'll make it pretty. We're going to slant asymptote like this. In this case, it would be y equal to 1/2 x minus 3. Again, I recommend reviewing your long division to do that, but we're not going to include it in the video here. So hopefully this has been somewhat helpful. Please ask questions if you have them. I'm more than happy to help. And that's it for now. If you want to know how this connects specifically to end behavior, because there's a particular notation, I'll skip to that here in just a second and you can look at that. Basically, it's the same slide, but you can see that if you have a horizontal asymptote at y equals to 0, then this is how you would write your end behavior, right? It's going to go to 0. If you have a horizontal asymptote at y equals to 2, then you're going to write your end behavior as y goes to 2. And if you have a horizontal asymptote like this that has, there's a slant asymptote, to me this gives so much more information than end behavior, but a line's going to, in this case, I don't have this quite right. As it goes to positive infinity, then this is, this side's negative infinity, this side's going to go to positive infinity, where I have some room. As x goes to positive infinity, that's this side. Y goes to negative infinity, and as x goes to negative infinity, that's this side. Y goes to positive infinity. So that's the correction to this. Ignore that there. Whoops. All right. Well, hope you guys got something out of this, and have a great day.